As a corollary of Minkowski's convex body theorem, let's talk about the Hermite theorem, which actually serves as a motivation for the Minkowski's work. Hermite's theorem states that if A is an n by n positive definite real symmetric matrix, then there exists a non-zero point x in Zn such that the quadratic form x transpose Ax is bounded by some constant c sub n times the determinant of A raised to the power 1 over n, where c sub n is equal to 4 over pi times n divided by 2 factorial raised to the power 2 over n. Actually, this constant is given by Minkowski. Hermite gave another constant. I'll talk about later about the comparison of Minkowski's constant and Hermite's original constant. So here's the proof due to Minkowski. As a corollary of his convex body theorem. Okay, now let's first make the following claim. The set of points x in Rn where x transpose times A times x less than or equal to rho is a compact symmetric convex set. Here by symmetric, we really mean it is symmetric about the origin. So now let's verify this claim. Which one of those three properties do you think is easiest to check? I think it is a symmetry about 0. For any x such that this product is less than or equal to rho, we have that immediately negative x transpose times A times negative x is equal to x transpose A times x. Which is less than or equal to rho. So this shows that negative x is also in this set if x is. So this shows that this set is symmetric about the origin. As next, we're going to show the compactness. First, it is easy to show that this set is closed. This is because this quadratic form is continuous with respect to x. So the quadratic form being less than or equal to rho as a closed subset in R. So if you consider this as a real number, this real number is less than or equal to rho, is a closed subset of R, has a pre-image in Rn as a closed subset by the continuity of the quadratic form. So this guy is closed. And now it suffices to verify that this subset is bounded in Rn. This is the place that we are going to use this hypothesis seriously. Since A is positive definite, real symmetric, we can write A as OT, the diagonal matrix with the eigenvalues of A on the diagonal, times O, where lambda sub i's are all positive. Because A is assumed to be positive definite. So, as a result, you can rewrite this subset as x in R, where xt, ot, this diagonal matrix, O, x, less than or equal to rho. And now, if you do a change of variable, if you take vector y to be equal to O times x, remember here O is n by n orthogonal matrix. It follows that this set can be written as, so this x will be equal to O inverse times y, and this will be written as yt times this diagonal matrix times y being less than or equal to rho. And now you can pull this O inverse outside. Notice that this part will be simply lambda 1 times y1 square plus the lambda n times yn square. Since we assume that lambda sub I are positive, which follows from the hypothesis that A is positive definite, we have from here that y sub I square is bounded by rho divided by lambda sub I for any I greater or equal to 1, less than or equal to n. This inequality tells you that the normal of y has an upper bound, which tells you that this subset is bounded. And now you do an orthogonal transformation of a bounded subset that still gives you a bounded subset in Rn. So the subset defined through a positive definite real symmetric quadratic form is bounded. So it is closed and bounded, so it is compact. So now we have checked that it is symmetric and compact. it remains to show that it is also convex. And to this end, we are going to use this relation that we just derived. This set is equal to O inverse of points y in Rn such that lambda 1 y1 square plus lambda n yn square is less than or equal to rho. I claim that this part is convex. Why? When n is equal to 2, you can easily see that this gives you an ellipse in the plane. But we shall do this more rigorously. So let's check it. For any vector y1 through yn and a vector with component z1 through zn in this set. Let us denote this guy by E. So for any two vectors in E and any mu between 0 and 1, we consider mu times y1 through yn plus 1 minus mu times z1 through zn. So this is component-wise mu y1 plus 1 minus mu z1, and the last component is mu yn plus 1 minus mu times zn. And now we make the sum lambda 1 times the square of the first guy plus lambda n times the square of the last guy. And we break this up. There will be three parts. The first part will be mu square times lambda 1 y1 square plus lambda n yn square. And the last part will be 1 minus mu square times lambda 1 z1 square plus lambda n zn square. And the guy in the middle will be 2 mu times 1 minus mu times lambda 1 y1 z1 lambda n yn zn. And now do you see how to deal with this part? This should be very elementary. So if you don't see it, you just move this 2 to here. Now this guy is bounded about by lambda 1 times y1 square plus z1 square plus lambda n times yn square plus zn square. Okay, now you know this part. By our assumption that those two vectors are in E, this part is less than or equal to rho. And this part is also less than or equal to rho. How about this part? This part is less than or equal to 2 times rho. So the whole thing here is less than or equal to mu squared rho plus 1 minus mu squared rho plus mu times 1 minus mu times 2 rho. So this gives you the square of mu plus 1 minus mu times rho, which is rho. So we proved that any such linear combination of those two vectors in E must also be in E. And this proves the convexity of E. Now the set we are dealing with is actually a linear transformation of E. And you know any linear transformation of a convex set is also convex by the linearity of this map. So it follows that the set defined through the quadratic form of a positive definite real symmetric matrix is convex. And we are done with this claim.